Hello, my name is Matthew Petter, and this is my final year project on IP hopping spread spectrum, or what I call Spectre. The contents of this presentation are introduction, the technologies that I used when building and testing Spectre, related works related to IP hopping and similar technologies, as well as other technologies that impacted the building of Spectre. The implementation or the experiments that I ran to test the future implementation of Spectre, the results of that implementation, and my final conclusions. For the introduction, the goal of IP hopping spread spectrum, of what I'm going to call Spectre from now on, is to mitigate an attacker's chance at gaining access to the network, intercepting traffic, or conducting a DDoS attack. The DDoS attack or a DOS attack is a denial of service attack or a distributed denial of service attack. That type of attack is where a single computer or multiple computers attempt to overload a network's resources in order to keep others from having access to that resource, and also possibly crashing the server or network in the process. This is done by keeping the IP addresses of all devices on the network in Spectre hidden and random, or pseudo-random. Spectre will be the pseudo-random distribution and rotation of encrypted IP addresses to clients on a network using Stream Control Transmission Protocol, that is SCTP, to connect the devices using multiple IP addresses at the same time. This is called multi-homing. IP addresses will be rotated through the list at certain times, one at a time, allowing the devices to remain connected while the rotating IP addresses change. So the technologies that I've used, I will cover in more detail in this section. The first technology is the Stream Control Transmission Protocol, SCTP, the Linux SCTP kernel module, Amazon Web Services, Python, VMware, and Wireshark. SCTP, or Stream Control Transmission Protocol, is an internet protocol on port 132 for establishing multiple connections between two endpoints for transmitting data. This is done using multiple streams at the same time. Some of the key features, especially the key features that pertain to Spectre, are multi-streaming, which is a sharing of a data load over multiple streams instead of just one socket like TCP. Multi-homing, which is multiple IP addresses assigned to one device between the client and the server. That means that one client may have up to 3 or 4 IP addresses assigned to that one device. Initiation protection, which is a 4-way handshake instead of a 3-way handshake, which we will cover later on. The main function of it is adding a cookie to the init ACK, which is echoed by the client to ensure verification of the connection. The last key feature is a graceful shutdown. It's where SCTP does not wait for the full finish signal from the client and instead shuts down completely after the shutdown acknowledgement signal. And there's a diagram later on in the presentation to describe the graceful shutdown and the 4-way handshake and multi-homing. The next technology I used was LKSCTP, the Linux kernel module. It is a C language library that allows a user to interface with the native SCTP in Linux. Linux automatically has native SCTP support, but the Linux control module allows a user to interface with it more easily. It has multiple different packages in it written in C that you can run as scripts in order to better use SCTP with easier function. This package includes changes to sockets not already present natively, utilities, tests, and other applications that use SCTP. The next technology is AWS, which is a web service that allows for users to launch multiple Linux EC2 instances. The instances that I used were designed to allow traffic through SCTP, which is port 132, HTTP and HTTPS. This is also used to test the live functionality of SCTP connections between two different machines that are completely separate from each other, with the exception of the SCTP connection. The other technology I used was a Python script. It's a Python script that I wrote that allows semi-automated commands to AWS Linux instances. I could launch instances, SSH into instances, SEP files into instances, and get the status of instances and terminate instances. This was modified to automatically install needed modules and other software that's required for the Linux SCTP module to function. Another technology that I used was VMware, which is used to install multiple instances of virtual machines into one system. I used this to launch an Ubuntu operating system and test the Linux SCTP module in a controlled environment before moving to a live environment, just to make sure that the module functioned properly. And the last technology that I used was Wireshark. Wireshark is a network analysis tool used for inspection of networks and protocols in very great detail. I was able to capture all of the packets and other network information sent through SCTP between the two machines. And this was either sent to a file or displayed to the user in real time. This was displayed to me in the implementation in the console. For the related works, this is the IP fast protocol design. It is a defense against DDoS attacks by hopping through IP addresses, which is similar to Spectre. It's also similar to frequency hopping spread spectrum, which is what radio systems use, and Bluetooth uses to hop between frequencies to ensure that the frequency could not be interrupted or intercepted. The server holds a random IP address for each client in a certain moment of time, so that for an outside observer, the data flow would look as if the client is connecting to a number of independent terminals. This mainly focuses on the defense during a DDoS attack, but it does not rotate through these IP addresses at any other time except during an attack. So it would have to detect an attack first before it starts its IP hopping. One of the limitations that I found was that it hides the real IP behind virtual IP addresses instead of actual physical IP addresses, which is something that could easily be circumvented. Another related work is Mirage, which is similar to the IP hopping one. The server acts as a secure gateway and calculates a function using the server's IP address in the current time. When the server shares this function with approved clients, who can then find the IP address of the server by using the same calculation. It's protected using a secure key distributed to the connected clients using AWS, Akami, DNS, or other services. Some of the limitations that I found was that it uses a separate service to distribute keys, which is it's a point of failure if that service is compromised or if the keys are compromised in between while they're sending the keys to the other clients. Another limitation that they talked about in the paper was network synchronization and resource management. In order for the server to act as a secure gateway, the time had to be synchronized with the clients, and network synchronization was an issue in this one as well. Another related work, not to IP hopping, but to DDoS protection, was Cloudflare. Cloudflare is well known for their DDoS protection softwares, as well as web hosting. And they're a network that moves content closer to the client while reducing server load latency and improving load times. It's considered much safer and more reliable between the server and the client. It uses something called an edge server, where a server is located at the physical edge of a network, which gives a shorter route through the network to the server that the client is searching for. It has an automated DDoS detection software for larger DDoS attacks. One of the biggest limitations that I found was that the automatic protection is only used for larger attacks, and it required manual client activation for any attacks that were perceived by the client. It doesn't detect those types of attacks automatically. This is the implementation portion, and there are 5 basic steps to the implementation. Cloning of the Linux kernel module to the Ubuntu virtual machine, configuration and installation of the kernel module, testing of the kernel module in the virtual machine, configuration and installation of the module on 2 different EC2 instances, and testing of the module connection and communication between those instances. Implementation was very simple. It was using a GitHub file. So I just cloned it into the Ubuntu virtual machine using Git, and the folder was there in my downloads. For installation of the Linux kernel module, there were already commands that were included in the README file and installation file that were inside of the kernel module folder downloaded from GitHub. The commands used were cd into the module folder, run bootstrap, run configure, and then run make. The commands may need to be preceded by sudo to fix any permissions issues, which I did have. I ran into an error when I was trying to install the module, so just run sudo before that and it works. For testing the Linux kernel module, it comes with a few pre-configured tests written in C included in the func test folder. These tests are an IPv4 test and an IPv6 test, both of which ensure the proper functions of SCTP on Linux. To run these commands, all you do is cd into the folder and use make v4 test and make v6 test. Once these tests were complete and they passed, I could move on to installing the Linux kernel module into the EC2 instances. For installing the Linux kernel module into EC2, the first thing I did was create a security group in AWS that allowed for SCTP traffic, which I will show later on, and HTTP and HTTPS traffic. I then edited the Python script to allow for the security group that I created on the instance launch, and it also allowed for a few pre-configurations that I added to make the use of the Linux kernel module easier. I then launched the 2 instances and SSH into each instance using the Python scripts that I wrote. I then cloned and installed the Linux kernel module in the same way that I installed them into the Ubuntu virtual machine. The steps were exactly the same, and the folder was located in the exact same place. For the testing of the Linux kernel module, there were 2 commands that I wanted to test in order to test the actual connections. One of the commands was sctp darn, which opens a link between the instances and allows for a message to be sent from the client to the server, and sctp test, which sends a small amount of packets through sctp between the client and the server. All of this traffic was captured using Wireshark. This is the testing of the sctp darn command. The screenshots are a little bit hard to see, but I can actually show better on the demonstration after the presentation. First step is one of the machines is set up to use Wireshark. In order to use Wireshark with the console, you had to use Tshark, which is still Wireshark. It's filtered to use SCTP, as can be seen here. The next machine is set up to use this command, which is the listening machine. It uses a local IP and a local port. And it doesn't need the remote IP and remote port because the sending machine will send directly to it. That's the other machine, which is the client machine. This is configured using this command. It contains a local IP, local port, remote IP, and remote port. The remote port will be the server. Then you type a message, if you can see it, into the first machine, the client machine, and it is printed out on the listening machine on the server. This is now testing the sctp test command. Again, the screenshot's a little bit hard to see, but I can go over them during the demonstration. This is used for sending a constant amount of packets through sctp to a listening server. This is for a more constant connection between the server and the client, just to test that the connection would stay open and that it would receive and then close out the connection. One machine is set up as a client to send the traffic. The second machine is set up as a server. Both of these commands are almost identical to the original commands, with the exception of SCTP test instead of SCTP darn. And then either machine is set up to run Wireshark in the background using the same filter to capture the SCTP traffic. As shown here, which I will be able to show during the demonstration as well, the four-way handshake and the graceful shutdown are clearly observed in the Wireshark logs. The results will be covered in these 5 sections, each detailing the features and limitations of SCTP and how they will function in Spectre. First, the four-way handshake, then the graceful shutdown, multi-homing, IP hopping and rotation, and then the limitations. For the four-way handshake is extremely reliable and secure compared to the normal TCP three-way handshake. It's able to verify its connection to the client before the full connection is established by using a cookie which contains a message authentication code, which is created by the server at the same time that the cookie is created, using a secret key. Only the server knows this secret key. The four-way handshake was, as said before, clearly observed functioning properly during the experiment. And shown here is the four-way handshake. The image is a little bit blurred, but as you can see right here, this is a TCP three-way handshake where there's a SYN, acknowledge, and then an acknowledge, and it connects. Whereas with the SCTP four-way handshake, it uses init ACK, a cookie echo, and then a cookie ACK. So it sends the cookie, it echoes back the cookie, and then acknowledges the cookie. The first cookie is sent in the init ACK from the server. The client has to echo the same cookie, and then the server acknowledges that the cookie is correct. It's a very secure way of connecting, and it will not connect if the client does not have the correct cookie. For the graceful shutdown, is a very important part of Spectre. It will allow the function of the IP rotation to work properly without any issues or lag time. It allows for a quick disconnect of the IP addresses. It works both with a shutdown signal as well as an abort signal. So even if the connection is shut down very quickly without a shutdown signal, it still uses an abort signal in that case, which also results in a graceful shutdown. For TCP, you have to get a FIN signal, acknowledge signal, and then the peer also sends another FIN signal, and then they acknowledge it. Whereas for the SCTP connection, it sends a shutdown or an abort signal. The shutdown signal is acknowledged, and then it completes the shutdown. As soon as it completes the shutdown, the connection is completely terminated. It doesn't have to wait for an acknowledgement. For multi-homing, unfortunately in this presentation, I wasn't able to get multi-homing fully functional, but multi-homing allows for multiple IP addresses to be connected between the client and the server. But despite this, the results that I've already gotten from the other functionality presents a very promising future for Spectre, and I will continue to work on multi-homing to get it functional. This is a diagram of how multi-homing works. For TCP, there is one connection between the client and the server, and there's the network in between. However, for SCTP, you can have multiple connections between the client and the server. And in the next slide, I will go over how the IP rotation works with more than just 2 connections. I will be using 3 connections, and I have a few diagrams there to show how it works. For IP hopping, because I wasn't able to get multi-home connections working, I was not also able to get IP hopping working. However, multi-home connections in IP hopping will be immediately dropped during an attack or during a rotational period and rotate to a new IP address, allowing for the other connections to balance out the network load. The diagrams here will show how the IP rotation will work. So for the first one, there are 3 connections between the client and the server. Each of these IP addresses share a load, and they're also backed up by each other. So even if one of these connections is dropped, there is no data loss. Upon a detection of an attack, or even just during a normal rotation period, Spectre will drop the first connection here, and allow the others to share the rest of the load, shown in the bigger arrows here. This should be seamless, although I will cover some of the limitations of this later on. Once the new connection is established, shown as connection 4, the next connection, shown as connection 2 from the previous diagram, will then disconnect. That's during a normal rotation period. During an attack, it will go ahead and rotate through the IP addresses rapidly, even if it's not on a certain schedule, and disconnect all of them and recycle all of those IP addresses. There are some possible limitations to Spectre, and these are all based on theory while working on this research assignment, as well as research into other related works such as Mirage and the IP hopping work. One of the possible limitations is some lag due to IP allocation and rotation in real time, because the server will have to allocate these IP addresses and rotate through them and in real time. There may be lag with the connection. Another limitation that I found was that new machines will have to be added into the rotation, which may prove time consuming and also cause possible synchronization issues. This will have to be researched later on more fully. Another limitation is that no testing has been done on other systems, with an exception of Linux machines. I was unable to find any implementation of SCTP in Windows or Mac, but since Mac is Unix-based, it's possible that it's easier to implement on Mac. Another limitation is a possible slower bandwidth due to the constant IP connection and disconnection. This may be minimal due to the fact that the other IP addresses are sharing the load. Another small limitation is that SCTP is not yet mainstream due to the fact that TCP and UDP are very popular, and they're the main types of protocols used at this time. SCTP has been around for a long time, but TCP and UDP have been proving more popular. And in conclusion, Spectre is still a work in progress, and it needs more research. The theory of the technology, along with the documentation and related works, seems to stand up on its own. This technology doesn't rely on any third-party sources for any security or detection methods, and it allows for more customization by the user or by the client over the technology. It's very robust and secure since it uses SCTP, and it allows for more reliability over normal TCP or UDP connections. There are some limitations, some of which have not yet been tested or found, but the technology has a lot of room to grow and improve. These conclusions are drawn from documentation of SCTP and its functionality, as well as theory and other research on related works on how they work together. Spectre is not being presented as a full replacement for other technologies, but a possible viable alternative without the need for large third-party sources for security. For my demonstration, I will be using a Ubuntu virtual machine in VMware, and shown here are my scripts. Some of the main commands that I have in these scripts are to create an instance, list instances, terminate instances, SSH into them, and secure copy using SCP. First, I will launch the script. And as you can see, I have a list of the following, and I want to list the instances. I already have 2 instances running in AWS, shown here. Both of them are using the security groups, and this security group is allowing all traffic and SCTP traffic, just to make it a little bit easier, as I was having some trouble with the Ubuntu virtual machine. Going back to the instances, one is named client and one is named server, just to distinguish between the two so that I can keep track of which one I'm using for listening and which one I'm using for sending messages. I also have 2 terminals down here, one named client and one named server, just like the instances. These terminals will be used to distinguish between the 2 instances that I'm connecting to via SSH. This client test one is going to be used to listen via Wireshark, which is also already set up to be listening to SCTP. I will clear out of that, run that again, and I can SSH into each one. So first I will SSH into the client using the client IP address, and I will SSH into it, copy the IP address, and now I'm in the client. I already have the Linux kernel module installed, and if I go into the module, you can see that it's already configured correctly. In the source file folder is where we will find the func tests and the applications to be used with the testing and the experiments that I ran. So first I will cd into the apps folder, which is where these tests are done, the SCTP test script and the SCTP darn script. The SCTP darn script is the one we're going to be using first, and the SCTP test script is the one we're going to be using second. First, before I do that, I need to also launch my server. So I will launch my scripts, SSH into it, grab my server IP, paste that, and I'm in the server as well. I will then also run this for the client test, which will be using the Wireshark. And as you can see, I have the command ready, and it's now capturing using Wireshark for any SCTP traffic. So first we will move over to the server, where we will start the listening command. The listening command will listen for any messages sent over SCTP from the client. First we will set that to listen. And as you can see, it is SCTP darn listening. And in the client, we move over here, and the client will use this command with the send function, and it will send a message, any message that we typed in. So if we test 1, 2, 3, new connection, peer addresses, and it gives you the IP address. And if we go over to the server, you can see that it has connected via SCTP, and it has sent the message through SCTP test 1, 2, 3. Now going over to the client test, you can see in Wireshark that it used the init ACK, cookie echo data, and cookie ACK. That means that it has a successful connection through SCTP using the 4-way handshake. Also, every few seconds, it will also run a heartbeat acknowledge, heartbeat, and heartbeat acknowledge, just making sure the connection is still stable. If I go and I close one of these connections, say I close the client connection, and go over here, you can see the graceful shutdown, the shutdown acknowledge, and shutdown complete. And you can see which IP addresses they come from. This makes sure that there is no lag time waiting for another shutdown acknowledgement for it to shut down the connection. Since the Wireshark is still running on the client test, I can also use the SCTP test command to test a full connection using packets. It'll send a small amount of packets through to the server, and the server will listen for these packets, and it will capture these packets, and it'll give information on this. The Wireshark instance will also capture all of those packets as well, and it'll capture all of the network activity. So if we go to server first, I'm going to have the command already ready, and we will run the listen command with SCTP test. Now you can see here it's starting tests, it's opening the socket, and it's listening, and it's trying to receive packets. If we go to the client, I have my command already ready with the IP address and the remote IP address and the port. I'm using port 132. I'm going to press enter on that, and it will send a bunch of packets through SCTP to the server. And each of these is a different step, so it'll have 10 different sessions of sending packets, and then it'll close out automatically. Going over to the server, you can see that it has sent all of these packets, it's received all of these packets, it received 1 byte of information each, and it assigned an ID to each one. And then at the end, it gave a shutdown and it gave a complete. And over here in the Wireshark, you can actually see the data being sent from the client to the server, as well as the 4-way handshake right here, the data right here, and the graceful shutdown here. The results of the graceful shutdown and the 4-way handshake show very promising results, and it shows that SCTP has been functioning better than expected up to this point. There will be more research and development done in Spectre to get the multi-homing completed and to get the IP hopping completed. For now, thank you very much for watching this demonstration, and I hope it was very enlightening into the functions of SCTP and Spectre. Thank you very much.